Hi, my name is Astrid Dirkswager, and this is my Lab 2 magnitude of a bar field. So, the purpose of this lab. For this lab, I measured the distance dependence of the magnetic field due to a smaller bar magnet and compared the measurements to the distance dependence predicted by the equations for the on and off axis magnet fields derived from the Biot-Savart law. And then I was able to determine the magnetic dipole moment and magnetic field of the bar magnet. We also use GlowScript to visualize the on-axis and perpendicular magnetic fields. So, a sneak peek of the results. The magnitude of the magnetic moment was 2.43 am squared. The distance was 0.24 meters. The magnitude of B net at 45 degrees was 2.64 times 10 to the negative fifth teslas. And I also noticed that as the magnet field increases, the distance decreases. And for the system of the lab, it is the bar magnet, and then the surroundings was everything else included in the lab. So the main physics principles I used in this lab are listed here. I used the Biot-Savart law and distance dependence equation. With these fundamentals, I was able to calculate the magnetic dipole moment to use in the GlowScript code later on, and the magnetic field of the bar magnet. So, experimental setup. First, I downloaded the magnetometer app. Then I placed the bar magnet at the end of the ruler and moved the smartphone around to get the measurements provided by the app. And after that, I recorded the distance between the bar magnet and the magnetometer in the Excel sheet provided. So some assumptions about the lab is that there's should be no interference with the magnetometer, the measurements should be accurate, and the app and the phone should also be consistent. This is my Excel sheet for the data I collected. I took 3 distances for each of the magnetic fields and got the average for each of these fields. These values will be needed to calculate the magnetic dipole moment. And as you can also see in the graph, the slope is negative 3.211, which is n, and the intercept is negative 14.811, which is k, which will also be used later to find mu. And then in the corner, you can also see that it calculated the B net average to be 5.74 times 10 to negative fifth teslas. So out of the observation statements provided in the lab instructions, only 2 were true. That is, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnet field increases. This is the GlowScript code I used. As you can see, my magnetic dipole moment is inputted as 2.43. Then there is the function for the magnetic field that follows, and after that is the code for the observation locations with 2 on-axis and 4 perpendicular. And then following that are the codes to create the arrows to represent the magnetic field for on-axis and perpendicular. And then the last piece of code uses the average dperp from the data earlier to create the arrow to represent the magnetic field at 45 degrees from the axis. So this is the visual provided from the GlowScript code. As you can see, the arrows on axis are larger than the arrows that are perpendicular. Then the purple arrow represents B net at 45 degrees, where the distance is 0.24 meters, and it also gives us the location with the x and y coordinates and 0 as the z coordinate, and then it also provides the magnitude of the B net at that distance, which is about 2.64 times 10 to the negative fifth teslas. So these are the main results from the lab. Again, we calculated that the magnitude of the magnet moment was 2.43 am squared. The distance of the 45 degree arrow was 0.24 meters. The magnitude of B net at 45 degrees was about 2.64 times 10 to the negative fifth teslas. And some potential sources of errors was that the app may not have provided completely accurate results. There would be systematic errors with measurements due to human error and again the app, and then other magnetic fields could have been interfering. So the first what if question in the experiment, you oriented your setup so to compensate for magnetic north. What if you hadn't done that and had laid out your meter stick at home at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? If I would not have compensated for magnetic north, then the results would not have accurately represented the magnetic field of the bar magnet. It is important that the initial x component of the magnet is set to 0, or else the results would have considered the magnetic field changing the resulting magnitude. And for the second what if question, I would expect the measurements to double in value, but the direction of the magnitude and the orientation would remain the same.